Welcome to our humble video. We would like to introduce you to the MEG device and briefly explain how it works, what is the instrumentation that is used in this device, and where it is used. MEG is simply a representation of the magnetic signals of the brain. These signals are very small that it ranges between femto and picotesla. To put that in perspective, the Earth's magnetic field strength around 30 microtesla. MEG have advantages that differentiate it from the other devices. Like for example, it uses non-invasive technique. That means it doesn't need to enter the human body or the body get injected by substance to get effective results. Other example is that it provides a high spatial and temporal resolution. High spatial means the resulted measurements have a lot of details, and high temporal means that it can detect thousands of signals per unit of time. Now I would like to tell you more about the main principles of the biological system that the device measures. The chemical reactions in the neurons produce an electrical current. This current goes from the presynaptic neurons to the postsynaptic neurons. And when enough current passes through the neurons, it generates a magnetic field. And since these magnetic fields are very small, we use flux transformers.
Now I want to talk about the instrumentation of the device. Now the sensor that's used to detect the magnetic fields generated in the brain is called flux transformer. Now flux transformer consists of two coils, a large coil and a smaller coil. The large coil captures the magnetic fields immediately from the brain, and since there is a current flowing from the large coil to the smaller coil, a magnetic field is also generated in the small coil. Now this field is more compact and more dense, but it has the same strength of the magnetic field as that of the large coil, because the flux transformer does not actually amplify the magnetic field, but rather it amplifies the flux of the magnetic field, and thus comes the name flux transformer. Now to detect this dense magnetic field, transducer we call superconducting quantum interference device, or SQUID, is used. Now these squids operate at very low temperatures in order to ensure high conductivity. Now to create this environment for operating the squids, a cooling agent called cryogen is used, and in this case mostly liquid helium is used. As you can see here in the schematic, as you can see in the figure here, the squids are immersed in the liquid helium. As you can see in this, we mentioned before that the magnetic fields generated in the nerves are actually very small, and because of that they can be easily disturbed by other magnetic fields that naturally exist in the environment. So as a first step to remove these noises, we place the magnetoencephalography device in a magnetically shielded room, and this room is built using many layers, metal and usually aluminum. Now all the electronics related to the magnetoencephalography device, including the computer that's going to be used to process the MEG signal, are placed outside this room because these are also going to generate magnetic fields. Now we talked about the flux transformer. The flux transformer actually has many configurations. The most basic configuration is the magnetometer. The magnetometer consists of only one coil, and as you can see here, by placing the magnetometer near the electric fields generated, a current passes through this coil, and therefore also a magnetic field is generated. Now we talked before about the noise cancellation, and we talked about how we can use a magnetically shielded room to remove these noises. However, we still, even with the magnetically shielded room, we will still have some artifacts that's going to disturb our signal. Now, however, there will be still noises that are going to disturb our signal. And for this, to cancel these noises, we use other configurations such as axial gradumeter. Now, this configuration consists of two coils placed on top of each other, and these two coils are also placed near the magnetic field, and an electrical current is generated in both coils. And because magnetic field is inversely proportional to the distance, the magnetic field that's going to be generated in the lower coil is larger than the one that's going to be generated in the upper coil. Now, you can think of this configuration as a differential amplifier, but for the magnetic fields. Now, because the relationship between these two coils is differential, now these two coils are not only going to receive the magnetic fields from the nerve, but also the magnetic fields from the environment, which is considered noise. In this case, we assume that this noise is received equally by these two coils. Now, because there's a differential relationship between these two coils, the resultant magnetic field that is going to be on the output, of these two amplifiers, is going to be the difference of the magnetic fields which are generated in these two amplifiers, and thus we can cancel the noise, and we can have a magnetic field that's equal to the magnetic field generated in the nerve. The source of these artifacts can be the body movements or the magnetic fields generated in the cables that are used to connect the magnetoencephalography device. Now, another configuration is the planar gradumeter. In this case, the two coils are placed next to each other. Now, this is similar to the axial gradumeter. We also have noise that's going to create a magnetic field in these two coils, and the working principle of this gradumeter is the same as the axial gradumeter. The noise is received, and from using the differential relationship, the result that we are going to obtain is going to be equal to only the magnetic field of the nerve. Now multiple configurations are used together to create multiple systems for the magnetoencephalography. One of the system is electroneuromach system, and this system consists of 306 chips or channels. Now, in each chip there are two planar gradumeters and one magnetometers. Another system that's used is the CTF system. Some of these systems have 151 channels, another have 275 channels. And all of the channels in this system are actually planar axial gradumeters. And in this case, the axial gradumeters cannot be placed on the chips because of the natural axial configuration. Now, this is the basic schematic of the magnetoencephalography. As you can see here, we have the magnetoencephalography device with the flux transformers receiving the signals. Now, actually all the components from this point on are the same as that of the EEG, because actually the signal that's going to be obtained from the squids is actually a voltage signal. What the squid does is that it receives the magnetic fields and generate a potential on the other side, and it generates a potential on the output. Now this signal, this voltage signal, needs to be processed the same way as an EEG signal is processed, and for that we use the same components. And of course we are going to have an instrumentational amplifier at the output of the squid. So you might wonder, then why do we use MEG if the nature of the signal is the same? Actually, there is an argument about this topic. Some say that MEG should not be used in clinical applications. It can be used for research. It's good for research purposes, but EEG should be used instead in clinical applications. But others argue that MEG can give us better results. As we said before, that the spatial and temporal resolution of the MEG is much better than the EEG. Now this is a sample recording of the MEG. As you can see here, this shows the signals that are generated at certain areas of the brain. As you may have noticed, this resembles the shape of a person head.
MEG is not an imaging technique and it doesn't show the structure of the brain, so we can't know the origin of the signal. For that reason, it is often used with MRI to determine the region of the brain at which a certain signal originates. Here we would like to discuss why is it used and what are the applications. In diagnosis, it can diagnose tumors by detecting abnormalities in the brain activity, and it can improve the detection of potential sources of seizures for epilepsy patients by revealing the exact location of the problem. This can help doctors find the cause of seizures. In research, it can show us which part of the brain is active during a certain activity and which part is not active. And by integrating information in the computer, we can use it as an input to control mechanical and digital devices. For example, an index of the computer or a bionic arm can be moved by the MEG signals of the brain. Question 1. MEG deploys the blank generated in the nerves to record brain activity. And the answer is magnetic fields. Second question. MEG provides high blank and blank resolution compared to other modalities such as EEG. And the answer is spatial and temporal resolution. Like we said, spatial means that its resulted measurements have a lot of details, and temporal means that it can detect thousands of signals per unit of time.
To prevent magnetic interference, blank is used as a first measure. Now we said that to prevent the interference from the magnetic fields that naturally exist in the environment, we first place the magnetoencephalography in a magnetically shielded room. So to prevent magnetic interference, magnetically shielded room is used as a first measure.
Fourth question. Blank is used to lower the temperature of the operating temperature of the squids to increase the blank. And the answer is cryogen and conductivity. A good example of a cryogen can be liquid helium, and it is commonly used in this type of devices. First question. MEG is often used in combination with which of the following techniques in order to obtain a functional brain image? And the answer is MRI.
Flux transformer amplifies which of the following? Now we said that the flux transformer actually does not amplify the magnetic field. And of course it neither amplifies the current nor the potential. However, it amplifies the flux of the magnetic field since the magnetic field that is going to be generated in the small coil is going to be more dense. And this is suggested by the name flux transformer. What can cause the noise, magnetic interference in the MEG signal? Now, we said that there are naturally existent magnetic fields in the environment, and of these are the Earth magnetic field or the magnetic fields generated by the electronics that surround the magnetoencephalography device. Other sources of magnetic fields, such as the magnetic fields generated from the human body itself. There are going to be artifacts from simple movements. These artifacts are going to disturb the MEG signal. So here it says the Earth magnetic field, the operating electronics, the artifacts from ion hand movement, and MEG connecting cables. So the answer is going to be all of them.
The fourth question is, the most permanent application in diagnosis of MEG is the locating of, and the right answer is epilepsy seizures.
Are the following sentences correct or not? CTF system uses planar gradiometers as sensors. We said that the CTF system consists of channels, and in each of these channels there is actually an axial gradiometer, so it's false. The relationship between the two coils of the axial gradiometer is differential. Now we said that the result that we are going to obtain at the output of the axial gradiometer is actually equal to the difference between the magnetic fields generated in both axial coils. So the relationship is indeed differential. Now, the processing computer is placed in the same room as the magnetoencephalography device. Now, we said that we need to reduce the noise as much as possible. So everything that can generate magnetic fields is placed outside this room, including the electronics and components that are related to the magnetoencephalography. So of course it's false, and it's placed outside the room. Now the squids are used to further amplify the magnetic flux. Now we said that the magnetic flux is actually amplified by the flux transformer. The squids are used to detect the magnetic fields of the small coils of the flux transformer and convert this magnetic field into a potential on the other side of the squids. So of course it's false, and they are used to capture the magnetic fields and produce a voltage difference on the output. Now, the least efficient flux transformer configuration in terms of noise cancellation is magnetometer. Now, we explained how that the axial gradiometer and the planar gradiometer are used to cancel noises. Now, magnetometer actually has no means to do that. So it is indeed the least efficient flux transformer configuration in terms of noise cancellation. Now this is the end of our presentation. We hope you learned something. Thank you.